A future civilization could be thriving in the clouds of Venus. This is not a fantasy, but a concrete scientific vision for floating colonies high above our sister planet's scorching surface. By the end of this, you will understand exactly how humanity could build cities in the sky of another world. We will uncover the hidden layer of Venus where the temperature is perfect and the air itself can lift entire habitats. We will confront the immense challenges of engineering and human endurance and reveal why this cloud-covered world might hold a more promising future for us than the red sands of Mars. What does it truly mean for a species to leave its home behind? Venus presents a cosmic riddle of two worlds in one. It is a planet almost identical to our own in size and basic makeup, often called Earth's twin, yet it has become a vision of hell. On the surface, the temperature soars to nearly 900 degrees Fahrenheit, a heat so intense it can liquefy lead. The atmospheric pressure is 90 times greater than what we experience on Earth, a crushing weight equivalent to being a kilometer deep in our ocean. This is a landscape of scorching plains under a perpetual, suffocating blanket of clouds, yet travel upwards just 50 kilometers, and the paradox reveals itself. In this specific layer of the sky, the temperature range is suddenly familiar, from 30 to 170 degrees Fahrenheit, a spectrum that includes the very temperatures we enjoy in our own homes. The atmospheric pressure here, remarkably, is nearly the same as the pressure at Earth sea level. This is the sweet spot, a narrow, habitable band in an otherwise lethal environment. It is this stunning reversal of fortune, from unimaginable hostility to surprising hospitality, just a short climb above the surface, that forms the entire foundation for a city in the clouds. This remarkable band of sky offers more than just comfortable temperatures. It presents an environment where the very air could do the heavy lifting. The key lies in the composition of the atmosphere itself. While the Venusian air is overwhelmingly carbon dioxide, this gas is much heavier than the nitrogen and oxygen mixture we breathe on Earth. If you were to fill a balloon with our own breathable air on Venus, something extraordinary would happen. That bubble of Earth-like air would act like a hot air balloon does in our own sky, because it is fundamentally lighter than the thick carbon dioxide surrounding it. It would experience a powerful buoyant force, rising naturally and wanting to float. This is not a minor effect. The lifting power of breathable air in that specific atmospheric layer is so strong that every cubic meter of it could support about half a kilogram of weight. To put that into perspective, a volume of air roughly the size of a small bedroom could lift an entire person. This simple, elegant principle transforms an immense challenge, suspension, into a surprisingly straightforward solution. We would not need powerful rockets or complex anti-gravity systems to keep a habitat aloft. The planet's own atmosphere, if we use it cleverly, would hold our cities in the sky for free. This elegant principle turns our basic need for survival into the very engine of suspension. On our own world, lifting a balloon requires a special gas like helium, which is much lighter than our atmosphere. But the rules are completely different on Venus. Our breathable air, a simple mixture of nitrogen and oxygen, becomes the helium. Because the Venusian atmosphere is so incredibly dense with carbon dioxide, a bubble of our own Earth-like air would be significantly lighter. Encase that bubble in a strong, lightweight habitat, and it does not just hang in the sky. It wants to rise, pulled upward by a natural, constant force. You would not need to burn fuel or run powerful engines just to stay afloat. The planet itself would cradle the city, providing a stable, energy-free foundation high above the inferno below. This inherent stability is what shifts the idea from a wild dream into a plausible engineering project. With the fundamental problem of lift solved so elegantly, architects and designers are free to think creatively about the form these settlements could take. What would a city designed to live in the clouds actually look like? The architecture of these cloud cities would be unlike anything ever built on Earth. Picture vast, interconnected platforms, not rigid and heavy, but lightweight and flexible, designed to float like a fleet of colossal blimps. Each habitat module could be a geodesic sphere, its latticework frame made from advanced alloys or carbon composites, materials strong enough to hold their shape yet light enough to be buoyant, and critically, resistant to the corrosive touch of the sulfuric acid droplets suspended in the Venusian clouds. Within these protective shells, life would unfold in pressurized comfort. Imagine standing on a transparent observation deck, the city's outer skin revealing an endless, sunlit panorama of yellow and white clouds stretching to the horizon in every direction. These would not be merely functional outposts but homes. Inside, spacious volumes would be dedicated to living quarters, hydroponic farms growing fresh food under artificial suns, and laboratories peering out into this strange new world. Safety would be the cornerstone of every design choice. The entire structure would be a network of redundant cells, much like a honeycomb. If one module were ever compromised, its neighbors would seal themselves off automatically, isolating the damage and preserving the integrity of the whole city. This careful, layered design ensures that a single point of failure cannot doom the entire community, but a stable, breathable shell is only the beginning. To truly live, a city must consume a tremendous amount of energy. How could a settlement floating in the clouds of Venus possibly power itself? Powering a floating city demands an immense and constant flow of energy, a challenge that Venus solves with an almost miraculous gift. High above the surface, the colony would bask in perpetual daylight, while the planet's thick clouds create a permanent overcast below. At the altitude of our floating city, the sunlight is abundant and far more intense than what we receive on Earth. Venus orbits closer to the Sun, so its skies are flooded with nearly twice the solar energy, and because the planet rotates so slowly, a single day there lasts for months on end. This means a solar panel would not face the daily cycle of dawn and dusk we experience. It would generate a continuous, unwavering stream of electricity for 116 Earth days straight. Picture vast fields of lightweight, advanced solar arrays spread across the tops of the floating platforms, soaking up this endless golden glow. This power would run everything from the air recyclers and water purifiers to the lights in the hydroponic farms and the computers guiding the city. It is a nearly limitless source of clean energy, making the colony self-sufficient in its most critical need. But electricity alone cannot sustain human life. With power secured, the next great task begins, harvesting the very air around the city to create water, breathable oxygen, and even building materials. This city in the clouds would not merely import its lifeblood from Earth. It would learn to breathe the alien sky, transforming the hostile atmosphere into a source of survival. The Venusian air itself is a vast chemical reservoir, a treasure trove of the very elements we need to live. Advanced processing stations, acting like the city's lungs and kidneys, would draw in the thick carbon dioxide. Through a series of sophisticated chemical reactions, they would split this gas apart, capturing the precious oxygen for us to breathe and isolating the carbon, which could then be used for manufacturing or even as a base for growing food. The nitrogen needed to balance our air mixture is also present in the atmosphere, waiting to be filtered and collected, but the resource harvesting goes even further. Those infamous clouds of sulfuric acid, a seemingly lethal feature, become a potential wellspring. The same technology could break the corrosive acid down into its component parts, yielding life-giving water and useful sulfur. This concept is known as in situ resource utilization, a technical term that simply means living off the land, or in this spectacular case, living off the air. It is the ultimate form of recycling, turning the planet's greatest threats into the colony's greatest assets. With the fundamental needs of air, water, and power secured, the floating city shifts from a survival outpost to a potential hub of activity. What kind of economy could possibly thrive in this golden haze, justifying the immense effort to build here? The rationale for building a city in the clouds extends far beyond mere survival into a powerful economic proposition. The first and most immediate driver is science itself. A permanent floating laboratory would offer an unparalleled vantage point to study one of the solar system's greatest mysteries, the runaway greenhouse effect that transformed a world so similar to our own into a scorching hellscape. Understanding Venus is not just an academic exercise, it is a vital cautionary tale for Earth, providing us with critical data on climate processes that we simply cannot replicate anywhere else. Researchers could also probe the planet's bizarre geology, mapping its volcanic plains and fractured highlands from above, and perhaps most intriguingly, search for signs of life not on the surface, but within the temperate cloud layer itself, where some scientists speculate hardy, airborne microbes could potentially exist. This constant stream of unique discovery would justify the initial investment, but the long-term economy would need to stand on more than research alone. The Venusian atmosphere holds a treasure with immense future value: deuterium. This heavy form of hydrogen, far more abundant in the clouds of Venus than on Earth, is a potential fuel for the fusion reactors of tomorrow. Harvesting it could turn the colony into a vital energy resource outpost for a future interplanetary civilization. Furthermore, its location makes Venus a natural waypoint for solar system travel. Spacecraft could use the planet's gravity as a slingshot, saving enormous amounts of fuel on journeys to the asteroid belt or the outer planets, making the floating city a strategic port and refueling station. These scientific and industrial activities create a compelling chain of economic value, from pure knowledge to tangible resources and strategic positioning. Yet, the success of such an endeavor ultimately rests not on engineering or economics, but on the human spirit. How would people cope with living permanently inside a sealed habitat, forever floating in an unbreathable sky, completely isolated from the natural world of their home planet? Life inside this floating realm would challenge our deepest human instincts. We are a species born of solid ground, shaped by the rhythm of days and seasons, the feel of soil, and the vastness of a natural horizon. In a cloud city, every one of those anchors is gone. The ground is a deadly memory miles below, the sky is a perpetual, uniform haze, and the only world you will ever know is the one contained within the sealed walls of your habitat. This reality would forge a new kind of society, one built on an unprecedented level of cooperation and shared purpose. Survival would depend on it. Every citizen would understand that their own well-being is inextricably linked to the health of the entire community. Social structures would likely evolve to be highly collaborative, perhaps with a strong emphasis on collective responsibility and transparent governance, where every voice matters because every pair of hands is essential. The psychological weight of this existence cannot be understated. The island in the sky mentality, a feeling of profound isolation and vulnerability, would be a constant challenge to overcome. To combat this, the colony would need to cultivate a rich and vibrant internal culture. Imagine art that explores the beauty of cloudscapes and the physics of light, or music composed with the subtle, ever-present hum of the city's life support systems as its backdrop. Recreation would be reinvented. With no open fields, sports might take place in vast, zero-gravity chambers or involve complex aerial maneuvers within safe, enclosed volumes. Virtual reality could offer immersive escapes to the forests and beaches of Earth, a vital psychological tether to the home world. But the most crucial element for mental and social stability would be a powerful, unifying purpose. The community would need to believe deeply and collectively that they are pioneers on the frontier of human existence. They are not just residents, they are the architects of a new branch of civilization, the guardians of irreplaceable knowledge, and the key to humanity's future among the stars. This shared identity would be the bedrock upon which everything else is built. Yet, before a single person can gaze out at those endless clouds, we face the most monumental challenge of all, the logistics of construction. How do you build a city in a sky 50 million kilometers away, and how do you get it there? The monumental task of transporting a city across space begins not with a single launch, but with a quiet, robotic armada. Long before a human crew is even assembled, the skies of Venus would see the arrival of our mechanical scouts. These are not simple probes, but sophisticated, autonomous factories and analysts designed to do the groundwork. Imagine a fleet of specialized drones, some like high-altitude balloons the size of football fields, others as agile as aerial submarines, all deployed into that temperate cloud layer. Their first mission is one of intense, localized scrutiny. They would map wind shears with laser precision, measure the exact concentration of corrosive chemicals at different altitudes, and test sample panels of habitat materials for years on end, confirming which alloys and composites can truly withstand the long-term assault of the Venusian atmosphere. The most critical of these robotic precursors would be the resource harvesters. These machines would be the true pioneers, landing in the sky and immediately getting to work. Using advanced solar power, they would begin the slow, steady process of sucking in the thick carbon dioxide, splitting it into oxygen for future crews to breathe and carbon for future factories to use. They would process the sulfuric acid clouds, extracting every precious drop of water. Their goal is to create a stockpile, a waiting cache of the very elements of life, established entirely by machines. This robotic outpost becomes a beacon, a fully automated life support system humming away in the alien haze, proving the core technologies and preparing a landing gift of air and water for its human creators. But this entire fleet of robotic laborers, along with the first pieces of the habitat itself, represents an unprecedented mass that must be lifted from Earth. How do you launch what is essentially a small town into the void? Launching a city into the sky requires moving mountains, not across a continent, but across the void of space. The sheer mass of material needed for even a modest floating outpost is staggering, amounting to thousands of tons of habitat modules, life support systems, and robotic fabricators. To lift this from Earth's gravity demands a fleet of a new class of super heavy lift rockets, colossal vehicles designed for one primary purpose, carrying immense payloads into orbit at a feasible cost. The economics of this endeavor hinge entirely on reusability, where these giant boosters would launch, land, and launch again dozens of times, turning a single, impossibly expensive mission into a sustained, manageable campaign of deliveries. This interplanetary supply chain must operate with the precision of a Swiss watch, synchronized with the celestial clockwork that governs the orbits of Earth and Venus. A launch window, the period when the two planets are aligned for the most efficient flight path, opens only once every 19 months. Missing this brief opportunity would mean a delay of over a year and a half, making meticulous, long-term planning an absolute necessity. Each payload, carefully timed for these windows, would be a masterpiece of compact engineering. The sprawling habitats we envision would not launch as finished structures, but as tightly packed, inflatable cores and specialized manufacturing equipment. Once safely delivered into the Venusian sky, these seeds of a city would activate, unfolding and expanding to their full size, using advanced polymers and alloys that harden in place. This orchestration of colossal rockets, precise celestial timing, and self-assembling architecture represents one of the most ambitious engineering projects humanity could ever undertake. Yet, once the final module is in place and the life support hums to life, the focus shifts from building a city to building a society, to the daily rhythms and profound challenges of a community born in the clouds. The day begins not with a sunrise, but with the soft, omnipresent glow of the clouds. A colonist's first task is often a diagnostic one, a careful check of the habitat's outer skin for any sign of corrosion. This is a ritual of vigilance because the sulfuric acid droplets suspended in the air, while diluted at this altitude, demand constant respect. They might use small, agile drones that scuttle across the exterior, their sensors scanning for microscopic thinning in the advanced polymer alloys. Inside, another crew is monitoring the vast solar arrays that carpet the city's upper surface, ensuring every panel is angled to drink in the perpetual daylight. The hum of the atmospheric processors is the colony's heartbeat, a constant reminder that the very air they breathe is being pulled from the hostile sky outside, split into breathable oxygen and valuable carbon. A significant portion of the workforce tends to the aeroponic farms where food grows without a speck of soil. In these pressurized, mist-filled chambers, roots dangle in the air, nourished by a nutrient-rich spray, yielding lush greens and fast-growing vegetables under the precise spectrum of artificial suns. This is not just farming, it is a daily act of life support, a direct conversion of energy and chemistry into sustenance. Leisure here is a conscious effort to nurture the human spirit. After a shift, a colonist might retreat to a virtual reality suite, slipping into a simulation of an earthly forest with the scent of pine and the feel of virtual moss underfoot. Others might gather at observation decks not to see stars, but to witness the dynamic weather of their new home, the swirling, golden cloud patterns, and the occasional, spectacular displays of lightning that flicker through the deep haze below. Yet, underlying this routine is a culture of preparedness. Emergency drills are as regular as meals. The sharp, piercing sound of an alarm signals a practice scenario for a hull breach or a sudden power loss. Every colonist, regardless of their primary job, is trained to respond, to seal pressure doors and activate backup systems. This is because self-reliance is their ultimate shield. The colony cannot wait 19 months for a spare part from Earth. So, the most critical facility is the fabrication bay, where 3D printers, fed with carbon and metals harvested from the atmosphere, manufacture everything from a simple tool to a complex valve. This ability to create, repair, and adapt on site transforms the city from a vulnerable outpost into a living, growing entity. It is a continuous cycle of monitoring, maintaining, and manufacturing, all to preserve a fragile bubble of life in an immense and beautiful sky. The most critical tool in the colony's entire inventory would be the fabrication bay. Transporting every spare bolt, every circuit board, and every specialized valve from Earth is a logistical impossibility, a chain of supply that stretches 50 million kilometers and can snap with a single launch failure. Resilience, therefore, is not just a concept, it is a physical capability built around advanced manufacturing. The colony would be equipped with vast 3D printers and automated fabrication labs that do not rely on shipments from home. Instead, they are fed by the resources harvested from the sky itself. Imagine a printer head meticulously laying down a new pipe fitting, but the material it uses is not plastic from Earth. It is a high-strength polymer, its carbon backbone derived directly from the carbon dioxide sucked out of the Venusian atmosphere. For more robust components, the source of materials could extend beyond the sky. Metals like iron and nickel could be delivered not from Earth, but from asteroids nudged into orbit around Venus. These captured space rocks would be processed in microgravity smelters, their raw ores refined into pure metal powders, ready to be printed into a critical pump housing or a structural beam for a new habitat module. This is the ultimate expression of self-sufficiency. The colony would not just live off the land, it would grow from it, repairing itself, and even expanding its own structure using the very substance of its new world. This radical independence stands in stark contrast to the vision of settling another world, one we have dreamed of for generations. While we have been looking toward the red sands of Mars, a future in the golden clouds of Venus has been quietly taking shape, and the differences between these two futures could not be more profound. The choice between Venus and Mars is not a simple one, as each offers a completely different vision for our future. Mars calls to us with a familiar solid ground beneath our feet. Its day is only 39 minutes longer than our own, and its surface, while barren, is a landscape we can walk upon, but this familiarity comes at a steep price. The Martian atmosphere is a wispy veil, 100 times thinner than Earth's, offering no protection from the relentless cosmic radiation that bombards the surface. The average temperature is a deadly 81 degrees below 0 Fahrenheit. To live on Mars is to live underground or within heavily shielded habitats, with every walk outside requiring a full spacesuit, a constant reminder of the world's hostility. Now contrast that with the floating cities of Venus. There, in that temperate cloud band, you would not need a pressurized suit to survive the environment outside your habitat. The atmospheric pressure is so similar to Earth's that a simple oxygen mask and protective clothing against the acidic mist would suffice. More importantly, the 50 kilometers of thick atmosphere above the colony acts as a powerful shield, blocking the same solar and cosmic radiation that makes the surface of Mars so dangerous. The trade-off, of course, is profound. You exchange the psychological comfort of solid ground for the physiological safety of a shirt-sleeve environment. This stark comparison forces us to reconsider a fundamental question: what is more critical for long-term human settlement, a familiar landscape or a more hospitable environment? This debate extends beyond human comfort into one of the most profound scientific quests: the search for extraterrestrial life, a search that Venus itself may unexpectedly be poised to answer. This search for life forces us to reconsider what a habitable world even looks like. We have long imagined life requires a planet with a surface of liquid water and solid ground, but the clouds of Venus present a radical alternative, a floating biosphere. The stunning discovery of phosphine gas in that temperate cloud layer sent shockwaves through the scientific community. On Earth, phosphine is a gas that is almost exclusively produced by microbial life or industrial processes. Finding it on Venus, a planet with no known industry, immediately raised the electrifying possibility that we were detecting a biological signature. While the debate over that specific finding continues, it powerfully underscores a single, transformative idea. The 50-kilometer high cloud deck of Venus is the only place in the entire solar system, other than Earth, where conditions might be right for life as we know it to exist. The temperatures are mild, liquid water could exist in the cloud droplets, and the chemical soup of the atmosphere provides potential energy sources. A floating city would transform this speculation into a direct, hands-on investigation. Imagine a laboratory module, its hull studded with specialized collection arms, gently descending just below the main platform to gather samples of the sulfuric acid mist. Inside, scientists would not be analyzing data from a distant orbiting probe. They would be peering through microscopes at the actual cloud particles, searching for the telltale shapes of microbial life or the complex chemical fingerprints of biological activity. Finding even a single, simple organism floating in those yellow clouds would be one of the most profound discoveries in human history. It would prove that life is not a unique miracle of Earth, but a common, tenacious force in the cosmos, capable of thriving in the most unexpected places. Yet, the moment we reach out to touch such a discovery, we are confronted by a complex web of questions that have nothing to do with science. Who has the right to search for life on another world, and what responsibilities do we bear if we actually find it? The moment we reach for another world, our hands are bound by invisible threads of law and ethics. The framework for our future in the clouds was written over half a century ago, in an era of satellites and moon landings. The Outer Space Treaty of 1967 forms the bedrock of international space law, declaring that no nation can claim sovereignty over the moon, a planet, or any other celestial body. This grand principle was designed to prevent a colonial scramble in the stars, but it leaves a critical question hanging in the Venusian air. If a nation cannot own Venus, can a company or a consortium own the resources it extracts from the atmosphere? The treaty is profoundly ambiguous on this point. It states that the exploration and use of outer space shall be the province of all mankind, but it does not explicitly forbid a private entity from setting up an atmospheric processor and harvesting deuterium or carbon. This legal gray area could become a battlefield of corporate and national interests. Who would grant mining rights in a sky that belongs to no one? A new interplanetary legal system would need to emerge, perhaps managed by a multinational body representing all of humanity, to ensure that the riches of this new frontier do not become the spoils of a few. But the legal questions are only half the story. The ethical considerations are even more profound and immediate. Our very presence in the clouds of Venus could irrevocably alter the one environment in our solar system, other than Earth, that might harbor life. Every breath of Earth air we vent, every microbe shed from a colonist's skin, and every droplet of water we release is a potential contaminant. If we discover a native Venusian microbe, how do we prove it is truly native and not something we brought with us? The scientific imperative to search for life clashes directly with the practical need to build a human habitat. This forces us to adopt a doctrine of planetary protection of unprecedented complexity. The floating city would need to function as both a laboratory and a quarantine zone, with some sections designated as pristine wilderness, completely off-limits to human presence and only accessible by sterilized robotic explorers. Establishing a fair legal framework and a rigorous ethical code is not a secondary task to be handled later. It is as fundamental to the colony's long-term survival as the integrity of its pressure hulls. Without clear rules for cooperation and a deep respect for the alien environment, our greatest achievement in the clouds could become our most tragic mistake. This careful planning extends beyond our first settlement, shaping the ultimate purpose of this new branch of human civilization. These floating cities could become the command centers for the most audacious project imaginable, the complete transformation of Venus itself. Terraforming would be a symphony of planetary engineering conducted over centuries. The first movement might involve unfurling a colossal solar shade at the point between Venus and the Sun where their gravitational pulls balance. This vast, gossamer-thin structure, perhaps built from asteroid material, would cast a permanent shadow, slowly cooling the planet's scorching surface over decades. As the temperature drops, the next phase begins, introducing a carefully designed cascade of genetically engineered microbes into the upper atmosphere. These microscopic pioneers would be programmed with a single, world-altering mission to break apart the thick carbon dioxide, locking the carbon away and releasing breathable oxygen. To deliver the oceans this world lacks, we might even guide ice-rich comets from the outer solar system, nudging them on a slow, deliberate collision course to crash into the planet and release their frozen water into the new, cooler environment. Our cloud city would be the beating heart of this millennia-long endeavor, a stable platform from which to monitor the slow-motion rebirth of a world, adjusting the process and managing the immense fleet of robotic workers required. This vision extends far beyond a single planet. A successfully settled Venus creates a strategic triangle of human presence, with Earth, Mars, and the floating cities forming a network of waypoints and resupply hubs. From this golden cloud base, missions could launch throughout the inner solar system with far less fuel, using Venus as a gravitational slingshot to reach the resource-rich asteroid belt or the mysteries of Mercury. Yet for all its grandeur, this vision is not without profound and vocal opposition. Is it our right to reshape an entire world, especially one that might already harbor its own fragile forms of life? This grand vision for a cloud-born civilization is not without its fierce and well-founded critics. The sheer magnitude of the technical challenges cannot be overstated. We are talking about constructing a habitat that must withstand a constant, insidious chemical attack. Sulfuric acid, even in a diluted mist, is relentlessly corrosive. The advanced polymers and alloys we rely on would be under a perpetual siege, requiring a level of material science we have not yet fully mastered. Every seam, every viewport, every external sensor would be a potential point of failure in an environment that offers no second chances. Beyond the physical structure lies the human element, a psychological hurdle just as daunting. How does the human mind cope with a life of perpetual confinement, where the only world you will ever know is a finite, manufactured bubble adrift in a golden haze? The profound isolation, the lack of natural seasons, the constant, low-grade anxiety of depending on flawless machinery for every breath, these are pressures we have never before asked a permanent population to endure. The financial cost to overcome these obstacles is almost beyond comprehension. The development of super-heavy lift rockets alone would require a global investment rivaling the Apollo program, and that is just the first step in a supply chain that spans tens of millions of kilometers. This raises a piercing moral question for our own world. Should we be spending trillions to build a city in the sky of Venus when our own planet faces crises of climate change, poverty, and resource scarcity? Is this a necessary evolution for our species, or a spectacularly expensive distraction from fixing the home we already have? These are not arguments to be dismissed, but essential parts of a sober, realistic conversation. Yet, in the face of these colossal hurdles, human ingenuity has already begun sketching the blueprints for a solution. The idea of cities floating in the Venusian clouds is not a new fantasy. Its roots dig deep into the pragmatic soil of 20th century science, back to a time when engineers first dared to sketch the blueprint for a cloud city. This vision was given a name and a serious technical foundation by NASA itself through projects like the High-Altitude Venus Operational Concept, or HAVOC. This was not a thought experiment. It was a detailed engineering study that asked a bold, practical question. How would we actually do it? The answer took the form of initial designs for massive, robotic airships that would pioneer the way, testing the environment and proving the technology long before a human crew ever left Earth. These historic blueprints envisioned habitats not as static platforms, but as dynamic vessels capable of navigating the high-altitude winds, using the planet's own weather patterns to stay aloft and in position. This foundational work demonstrates that the concept rests on decades of meticulous scientific thought and iterative design, transforming it from a wild speculation into a plausible, long-term goal for human expansion. The torch of this grand legacy is now being carried forward by a new generation. Private aerospace companies, unburdened by the shifting priorities of government agencies, are now injecting fresh momentum and capital into the dream. They are revisiting those classic airship designs with modern materials, advanced artificial intelligence for navigation, and new business models aimed at making the venture economically viable. This powerful partnership between the rigorous foundation of public science and the agile innovation of private enterprise is what finally brings a city in the clouds from the pages of a NASA, a study into the realm of tangible possibility. The legacy of NASA early blueprints is now being carried forward by a new wave of pioneers. The private space industry, once a distant supporter of government programs, has become the primary engine of innovation, and its ambitions are reshaping our interplanetary future. While the public gaze is often fixed on the red sands of Mars, the technologies being forged for that mission are building the very tools we would need for the golden clouds of Venus. Consider the reusable rocket. A company like SpaceX has fundamentally altered the economics of spaceflight by proving that a launch vehicle can be used again and again, much like a commercial airliner. This is not just a cost-saving measure, it is the foundational breakthrough for the immense, sustained supply chain required to build a city in the sky. The same heavy-lift rockets designed to carry crews to Mars could, with only minor adjustments, launch the prefabricated modules and robotic fabricators on a trajectory to Venus. The advanced life support systems being tested for long-duration Martian voyages are another perfect example. These are closed-loop ecosystems that recycle air and water with extreme efficiency, a technology that is not destination-specific. A habitat floating in the Venusian clouds would rely on the very same principles of sustainability and resource recycling. This technological convergence means that every dollar and every hour of research invested in a Mars mission inadvertently builds a part of the Venusian dream. But the private sector's role could become even more direct. As the concept gains traction, we could see the rise of specialized startups entirely dedicated to the unique challenges of atmospheric colonization. Imagine a small company focused solely on developing a new, acid-resistant polymer for habitat holes, or another perfecting autonomous drone systems for cloud mining. This kind of targeted, competitive innovation, driven by venture capital and the promise of being first to market, could solve specific problems at a speed that large, bureaucratic organizations cannot match. The involvement of private capital does more than just fund research. It injects a powerful sense of urgency and a competitive drive that can dramatically accelerate the entire timeline. The journey from a concept on a whiteboard to the first foundation module floating in the Venusian atmosphere could be cut from a century to a matter of decades. This public-private partnership will be absolutely vital, especially for developing the next generation of propulsion technology. The rockets that get us to orbit are one thing, but we need even more advanced engines to travel efficiently between worlds. Nuclear thermal propulsion, which uses a fission reactor to heat propellant for incredible thrust, is a prime candidate being explored by both NASA and private firms. Such a system could slash the travel time to Venus, reducing the radiation exposure for crews and the amount of supplies they would need to carry. This collaborative model, where government agencies set the grand vision and establish safety standards while private companies compete to build better, faster, and cheaper hardware, creates a powerful synergy. It is this combined force of public purpose and private ambition that will ultimately build the bridge between our world and the waiting skies of another. The journey itself becomes the next great engineering puzzle. While conventional chemical rockets could propel a spacecraft from Earth to Venus, they do so on a slow, economical trajectory that conserves fuel, a voyage stretching for many months. For a colony dependent on regular resupply and crew changes, that delay is a critical vulnerability. The solution lies in a new class of engines currently taking shape in research facilities. Nuclear thermal propulsion offers a revolutionary leap. Imagine a rocket where the fiery combustion of chemicals is replaced by the immense heat of a compact nuclear reactor. This reactor superheats a propellant like liquid hydrogen, blasting it out of the nozzle with far greater efficiency than any chemical reaction. A ship equipped with such a system could slash the travel time to Venus from half a year down to just a few weeks. This is not just about convenience, it is about survival. A faster transit means crews are exposed to the dangerous radiation of deep space for a much shorter period. It also means that a medical emergency or a critical parts failure on the colony could be addressed with a swift response from Earth, rather than a wait that could stretch past a year. Another promising technology, solar electric propulsion, uses massive arrays of solar panels to generate electricity. This power is then used to create and accelerate a beam of charged particles, providing a gentle but continuous thrust. While slower to accelerate than a nuclear thermal rocket, this system is incredibly fuel efficient, making it ideal for hauling large, unmanned cargo modules on regular supply runs. The development of these advanced drives is a tide that lifts all boats, benefiting missions to Mars, the asteroid belt, and beyond. But what about transportation once you are there? The local environment of Venus itself might offer a truly elegant solution for moving between different points in the sky. Harnessing the winds of Venus would become the colony's highway system. The upper atmosphere is a river of air in constant hurricane force motion, a phenomenon known as superrotation. These powerful winds complete a full lap around the entire planet in just 4 to 5 Earth days, creating a natural, high-speed conveyor belt circling the globe. To travel from one point to another, colonists would not fight this flow but join it. Their vehicles would be elegant, intelligent airships, more like graceful, winged whales than the rigid blimps of old. Crafted from advanced, acid-resistant materials, these vessels would use the wind itself for propulsion, deploying retractable solar sails to catch the endless daylight and make subtle adjustments to their course. A journey from a research outpost studying a colossal, continent-sized volcano to a mining station harvesting atmospheric deuterium could become a matter of a few days, a scenic voyage through the planet's eternal golden noon. This mastery of the skies would unlock the true potential of the Venusian frontier. Scientists could deploy fleets of smaller, autonomous gliders from a mothership, releasing them into different wind currents to map global weather patterns or sample the chemical makeup of the clouds across thousands of kilometers. Establishing a network of specialized outposts becomes practical when travel between them is measured in days, not months. One platform could focus on high-energy physics, using the intense solar flux, while another, drifting over the polar regions, could study the mysterious vortexes that swirl at the planet's poles. This interconnected web of floating stations transforms a single, isolated city into a truly planetary civilization. But before any airship can unfurl its sails in that alien sky, every component, from its navigation algorithms to the very fabric of its hull, must be proven in chambers that replicate the unique hell of Venus. We must build a piece of Venus here on Earth to ensure we can survive there. Our final proving grounds are not in space, but right here on our own planet. To prepare for the alien skies of Venus, we first turn to the high, thin air of Earth's stratosphere. Here, the conditions of pressure and temperature eerily mimic that 50-kilometer high sweet spot on our sister world. This is where engineers can deploy and test prototype habitat balloons, watching how vast, inflatable structures hold their shape and integrity in the near vacuum. It is also the perfect training airspace for the drones and robotic gliders that will one day navigate the Venusian cloud decks, allowing us to refine their autonomous navigation systems in a real but far safer sky. Back on the ground, another kind of test is underway inside sealed laboratories. Scientists create miniature versions of the Venusian atmosphere, pumping in carefully measured concentrations of sulfuric acid vapor. Into these corrosive chambers go sample panels of every potential habitat material, from experimental polymers to novel metal alloys. They are left for months, even years, under stress and exposure, all to answer one critical question: which one will last a lifetime in that acidic haze? Yet the most complex tests involve none of this hardware, but the human spirit itself. Isolated research stations, like the submerged Aquarius habitat or the remote outposts in Antarctica, become perfect stand-ins for the Cloud City. In these confined, extreme environments, cut off from the wider world, we study the psychological and social dynamics of a small crew living under perpetual pressure. How does group cohesion hold over a year-long mission? What routines and technologies best combat the sense of isolation? The data gathered here is priceless, helping us design not just a functional habitat but a livable home. Every innovation born from this terrestrial research offers a dual gift. The advanced acid-resistant coatings developed for a Venusian hull could lead to longer-lasting, more durable materials for our buildings and bridges on Earth. The hyper-efficient, closed-loop life support systems perfected for the Colonie could revolutionize how we manage water and waste in our own cities. The quest to build a future on another world invariably teaches us how to build a better one right here. The relentless pursuit of conquering the Venusian clouds would force us to master technologies with the power to heal our own world. Every material engineered to withstand that corrosive sulfuric mist could be adapted into a new generation of protective coatings. Imagine bridges, ships, and skyscrapers painted with paints derived from this research, their lifespans extended by decades as they shrug off the corrosive effects of rain, salt, and pollution. The very cars we drive and the pipelines that crisscross our continents could become far more durable, reducing the constant, costly cycle of maintenance and replacement. This drive for survival in an alien sky would gift us with a legacy of resilience for our infrastructure on Earth. But the benefits would reach far deeper than our city's skeletons. The Colony's most vital system, its closed-loop life support, is a perfect blueprint for sustainability. To survive 50 million kilometers from home, the city must recycle every drop of water and every breath of air with near-perfect efficiency. The technology developed to achieve this, the atmospheric processes that pull carbon dioxide from the Venusian sky and split it into oxygen and carbon, is a direct form of carbon capture. Scaled up and deployed across our own planet, these systems could actively remove the primary greenhouse gas from our atmosphere, turning a waste product into a valuable resource for manufacturing or even synthetic fuels. This is not just recycling, it is a fundamental rewiring of how we manage our planet's resources, moving from a linear system of consumption and waste to a circular one, just as a space colony must. The energy to power this entire closed-loop civilization would come from another transformative spin-off, The high-efficiency, lightweight solar panels and the massive energy storage systems required to harness Venus's perpetual daylight would push renewable technology to its absolute limits. The breakthroughs made there could solve the core challenges of our terrestrial energy grids, providing cheaper, more robust batteries to store solar and wind power for when the sun does not shine and the wind does not blow. This cascade of innovation, from tougher materials to sustainable systems and clean energy, demonstrates a profound truth. The greatest return on our interplanetary ambition may not be the resources we find out there, but the wisdom we bring back home. This entire journey, from a vision of floating cities to the tangible betterment of life on Earth, forces us to confront a much larger question about our species' ultimate destiny. This grand endeavor touches something far deeper within us than the practical problems of engineering or economics. We are driven by a force that has defined our species since we first looked up at the night sky, a restless need to cross the next horizon. Establishing a presence on another world is the ultimate expression of that ancient instinct. It transforms humanity from a single-point failure into a multi-planetary civilization, ensuring that the story of life and consciousness, which began here on Earth, does not end here. A cataclysm that might devastate our home world, whether natural or self-inflicted, would no longer spell the end for humanity. Venus becomes a second chapter, a backup of the biosphere, and a repository of all our knowledge, art, and culture. This is not about abandoning Earth, but about ensuring its legacy endures among the stars. The challenges of building a floating city push every facet of our capability to its absolute limit. It demands breakthroughs in material science that redefine durability, life support systems that achieve perfect recycling, and a level of international cooperation we have rarely managed to achieve. In striving to conquer this new environment, we are forced to become better engineers, better stewards, and better collaborators. The colony becomes a crucible, forging a new version of humanity equipped with the wisdom and technology to thrive in a universe that is largely hostile to life. This journey forces us to confront our place in the cosmos. Are we merely passengers on a solitary world, or are we the agents who will carry the spark of life outward? To choose the latter is to accept a cosmic responsibility, to believe that consciousness is not a random accident but a force with a purpose, one that seeks to propagate itself. The vision of a city floating in the golden haze of Venus is more than a feat of engineering. It is a declaration that our future is not bound by gravity or atmosphere, but only by the scope of our ambition and the courage of our spirit. The path to the clouds of Venus is not merely a choice of destination, but a fundamental test of our vision for tomorrow. We have explored a world where the air itself can lift our cities and the endless sunlight can power them, where the greatest threats of space are tempered by a thick atmospheric blanket. This hidden frontier offers a blueprint for a civilization that lives in harmony with a hostile environment, learning to breathe its sky and build with its own substance. It challenges the long-held assumption that our future among the planets must be dug into the red soil of Mars, proposing instead a society that floats gracefully in a golden haze. The obstacles are monumental, from the relentless chemistry of the clouds to the profound psychological weight of a life adrift. Yet, the potential rewards are equally profound, promising not just survival, but a new renaissance of science, industry, and human collaboration. The journey will demand the very best of our ingenuity and courage spanning generations, but the ultimate prize is a second home for humanity, a city of light suspended in the alien sky of our sister world, a permanent testament to our unyielding drive to reach for the heavens. So we leave you with this question. When you look up at the evening star, will you see a distant point of light, or will you see a future waiting to be built? Let us know your thoughts in the comments, and if you enjoyed this journey, subscribe for more explorations of humanity's next frontier.